The North Atlantic, March 15, 1943. 300 miles west of Iceland, the cold black waters rolled beneath a moonless sky. Captain Lieutenant Werner Hartmann stood in the conning tower of U-62, scanning the horizon through Zeiss binoculars that had served him through 17 successful patrols. The periscope had been raised for barely 45 seconds when the first depth charge exploded 200 yards off the starboard beam. The shockwave lifted the submarine's stern, throwing Hartmann against the tower's steel plating. As klaxons screamed and crew members scrambled to diving stations, he caught a glimpse of the aircraft banking sharply overhead. A British Liberator, its white undersurface barely visible against the overcast sky. But something was impossible about this attack. The U-boat had surfaced under complete darkness. No moon, no stars, cloud cover at 800 feet. Hartmann had chosen these conditions specifically because they made visual detection from the air virtually impossible. Yet the British bomber had found him with surgical precision, as if guided by an invisible hand directly to his exact position. As U-62 dove beneath the surface and the depth charges continued to bracket their position, Hartmann realized that every assumption he'd been taught about submarine warfare had just become obsolete. The British weren't hunting by sight anymore. They were using something else. Something that could see through darkness and clouds and detect a submarine's periscope from distances that should have been impossible with existing technology. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The question that would haunt Hartmann through his remaining patrols and eventually into captivity was brutally simple. How could an aircraft spot a periscope in total darkness from 8 miles away? The answer represented one of the most consequential technological secrets of World War II, a breakthrough that German naval intelligence never fully understood until after the war ended. The Allies had developed centimetric radar, specifically 10-centimeter wavelength systems that could detect objects smaller than a human being from distances that rendered U-boat tactics completely obsolete. The story of how this technology turned the Battle of the Atlantic begins not with dramatic naval engagements, but in the physics laboratories of Birmingham University, where researchers were pushing the boundaries of electromagnetic radiation in ways that would fundamentally alter the nature of maritime warfare. The transformation from meter-wave radar to centimetric systems represented a quantum leap in detection capabilities that German intelligence dismissed as technically impossible until photographic evidence proved otherwise. Hartmann's experience in March of 1943 was being repeated across the Atlantic theatre as U-boat commanders discovered that their carefully refined tactics for evading Allied detection had suddenly become death traps. The periscope depth approach that had allowed submarines to observe convoy movements while remaining invisible was now broadcasting their exact position to aircraft equipped with radar systems operating at wavelengths the Germans couldn't detect or jam. The psychological impact on U-boat crews was devastating. Submariners who had survived dozens of patrols through skill and careful adherence to proven doctrine were being depth-charged by aircraft that appeared out of nowhere in conditions that should have made air patrol completely ineffective. The mathematics of submarine warfare that had governed German tactics since 1939 had been rewritten by British scientists working with electromagnetic principles that Kriegsmarine intelligence officers believe were practically achievable. Professor John Randall examined the cavity magnetron prototype at Birmingham University in February of 1940, holding in his hands a device that would eventually cost tens of thousands of German submariners their lives. The magnetron was a vacuum tube that generated microwave radiation at wavelengths measured in centimeters rather than meters, enabling radar systems with resolution and range capabilities that exceeded existing technology by orders of magnitude. The theoretical physics underlying centimetric radar had been understood since the 1930s, but practical engineering challenges had prevented development of systems compact enough for aircraft installation. The breakthrough came through cavity magnetron design that generated sufficient power output at 10-centimeter wavelengths, while maintaining dimensions small enough for bomber installation. The resonant cavities machined into the magnetron's copper anode created standing wave patterns that amplified microwave oscillation through electromagnetic feedback, producing continuous wave radar signals with power outputs exceeding 10 kilowatts. The immediate application that British radar researchers identified was anti-submarine warfare. Meter-wave radar systems like air-to-surface vessel, or ASV Mark II, could detect U-boats on the surface at ranges of several miles, but their wavelength limitations meant they couldn't reliably detect periscopes or surfaced submarines in rough seas. The radar returns were masked by sea clutter, the electromagnetic reflections from wave crests that created false targets on operator screens. Centimetric radar operating at 10-centimeter wavelengths could distinguish between wave patterns and solid objects with unprecedented precision. The physics were straightforward but revolutionary. Shorter wavelengths meant narrower radar beams that could be focused with smaller antenna systems. The 10-centimeter wavelength allowed radar dishes measuring just 30 inches in diameter to achieve beam widths of just a few degrees, providing angular resolution that meter-wave systems required antenna arrays measuring dozens of feet to accomplish. This compact design enabled installation in maritime patrol aircraft without compromising their performance or range. Dr. Edward Bowen led the telecommunications research establishment team developing the ASV Mark III radar system, incorporating the cavity magnetron technology. The engineering challenges were substantial. The magnetron required high-voltage power supplies, sophisticated cooling systems, and precision manufacturing that pushed the limits of 1941 industrial capabilities. The radar antenna needed to scan continuously while the aircraft maneuvered, maintaining target tracking through complicated mechanical gimbal systems that compensated for aircraft motion. The first operational test of ASV Mark III occurred in March of 1941, when a specially equipped Wellington bomber detected a submarine at a range of 7 miles, in conditions of complete darkness and heavy cloud cover. The radar operator observed a distinct return on his display screen that persisted through multiple scans as the aircraft closed the distance. The submarine, later confirmed to be conducting training exercises off the Scottish coast, had no indication it was being tracked until the Wellington dropped flares directly overhead. The strategic implications were immediately apparent to RAF Coastal Command leadership. For 3 years, U-boats had exploited darkness and weather conditions to surface for battery charging and transit across patrol areas with minimal risk of air attack. British aircraft had been largely ineffective during night hours, limited to random patrols over vast ocean areas with virtually no chance of detecting submarines through visual observation. Centimetric radar transformed maritime patrol aircraft into precision hunter-killers that could detect and attack submarines regardless of weather or lighting conditions. The technology transfer from experimental prototype to operational capability required massive industrial mobilization. The cavity magnetrons needed precision manufacturing with tolerances measured in thousandths of an inch. The copper anodes required specialized machining that only a few facilities in Britain could produce. The evacuation of air from the magnetron chambers demanded vacuum pumping systems that met specifications far exceeding normal industrial standards. By August of 1941, British manufacturers were producing magnetrons at rates sufficient to equip frontline aircraft, though production bottlenecks limited initial deployment to priority squadrons. RAF Coastal Command established training programs to familiarize radar operators with the unique characteristics of centimetric detection systems. The operators needed to distinguish between genuine submarine contacts and false returns from fishing, vessels, driftwood, and meteorological phenomena. The training emphasized rapid target identification and precise navigation to attack positions before submarines could dive beyond weapon range. The tactics developed during this training period would prove decisive as ASV Mark III systems entered operational service throughout 1942. German naval intelligence received initial reports of improved British radar capabilities in late 1941, but the information was fragmentary and contradictory. U-boat commanders reported being attacked by aircraft in conditions that should have made visual detection impossible, but the German technical experts dismissed these accounts as exaggerations or bad luck, rather than evidence of revolutionary radar technology. The wavelength physics that enabled centimetric radar seemed to require power outputs and antenna designs that German engineers believed were impractical for airborne applications. Korvettenkapitän Hans Meckel supervised radar countermeasure development at the Kriegsmarine's Technical Research Facility in Kiel, analysing intelligence reports about British detection capabilities with increasing scepticism. The claimed radar performance exceeded German technical assessments by margins that seemed physically impossible. German magnetron research had concluded that centimetric wavelengths required power levels unattainable with vacuum tube technology available in 1941. The intelligence reports suggesting otherwise were classified as probable misinformation designed to deceive German countermeasure efforts. This analytical failure would prove catastrophic for U-boat operations. While German engineers debated whether centimetric radar was theoretically possible, British aircraft equipped with ASV Mark III were detecting submarines with increasing efficiency. The gap between German intelligence assessments and operational reality widened throughout 1942 as U-boat losses mounted without corresponding increases in Allied convoy protection or surface vessel deployment. Something was killing submarines at unprecedented rates, but German naval leadership couldn't identify the threat they needed to counter. The Metabele incident of February 1943 finally provided physical evidence that German analysts could no longer dismiss. During a nighttime engagement south of Ireland, U-boat U-456 damaged the British destroyer HMS Metabele with a torpedo hit. As the destroyer began sinking, U-456 surfaced to assess damage and look for survivors. A British aircraft appeared within minutes and attacked the submarine with depth charges, forcing an emergency dive. When U-456 later surfaced after the aircraft departed, crew members recovered debris from Metabele, including electronic equipment fragments. German technical intelligence examined the recovered components and identified cavity magnetron remnants that conclusively proved British forces were operating centimetric radar at sea. The wavelength calculations indicated systems operating around 10 centimeters, exactly the frequency range that German experts had assessed as impractical for operational deployment. The intelligence report reached Admiral Karl Dönitz, commander of the U-boat force, in early March of 1943, the same month that Kapitänleutnant Hartmann experienced his impossible detection west of Iceland. Dönitz ordered immediate tactical changes to U-boat operations, but the directives revealed how completely German naval strategy had been compromised by Allied radar superiority. Submarines were instructed to minimize periscope exposure, limit surface time to absolute minimums, and avoid areas where aircraft patrol was probable. These defensive measures acknowledged that U-boats could no longer operate with impunity during darkness or poor weather. The initiative in the Battle of the Atlantic had shifted decisively to Allied forces, who could now hunt submarines with technological advantages that German countermeasures couldn't neutralize. The human cost of Germany's radar intelligence failure was measured in thousands of submariners, who died because their commanders didn't understand they were being tracked by systems that rendered traditional evasion tactics useless. The sophisticated wolfpack tactics that had devastated Atlantic convoys in 1940 and 1941 became suicide missions, as Allied aircraft could detect and attack submarine concentrations before they could coordinate. Attacks on merchant vessels. The technological revolution, represented by 10-centimeter radar, had fundamentally altered the strategic balance of the naval war. Flight Lieutenant David Walker reviewed the contact reports from his squadron's patrol area southeast of Greenland, noting patterns that indicated U-boat concentration along the convoy routes where merchant shipping was most vulnerable. His Liberator bomber was equipped with ASV Mark III radar that had proven extraordinarily effective at detecting submarines during the past 6 months of operations. The radar operator seated at the display console behind the cockpit had become the most critical crew member on anti-submarine patrols, more important than the bombardier or navigator for mission success. The ASV Mark III installation in Walker's aircraft represented the culmination of 2 years of engineering development and operational testing. The radar antenna was mounted in a retractable radome beneath the bomber's fuselage, providing 360-degree coverage as the dish rotated continuously during patrol operations. The display scope showed returns as luminous dots against a circular grid marked with range and bearing indicators. Experienced operators could distinguish between different types of targets based on the return strength and persistence across multiple radar sweeps. Walker's squadron operated from an airbase in Iceland that had been established specifically to provide mid-Atlantic convoy protection during the period when ships were beyond range of land-based aircraft operating from Britain or North America. The geography of the North Atlantic had created an air gap where U-boats could operate without significant risk of air attack, allowing them to concentrate against convoys with devastating effectiveness. The introduction of very long-range liberators, equipped with centimetric radar, had closed this gap, extending Allied air coverage across nearly the entire Atlantic convoy routes. The tactical procedures Walker's crew followed had been refined through dozens of patrols and represented the distillation of hard-won operational experience. The radar operator maintained continuous watch on the display scope, adjusting sensitivity and gain controls to optimize detection range while minimizing false returns from sea clutter. When a contact appeared, operator would call out range and bearing to the navigator, who would calculate an intercept course that brought the aircraft over the target position for visual identification and attack. The detection range varied based on sea conditions, target size, and atmospheric factors, but under typical North Atlantic conditions, the ASV Mark III could reliably detect a surfaced submarine at 12 to 15 miles. Periscope detection was more challenging due to the minimal radar cross-section, but the 10-centimeter wavelength provided sufficient resolution to identify periscope returns at ranges exceeding 8 miles when sea conditions were favorable. This detection capability gave Walker's aircraft enormous tactical advantages over submarines that had no idea they were being tracked until the attack commenced. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The typical engagement sequence began with the radar operator identifying a contact at maximum detection range. Walker would begin a descent from patrol altitude while maintaining course toward the contact position. At approximately 5 miles range, the crew would begin visual search procedures using binoculars to locate the submarine on the surface or identify the featherwake created by a periscope cutting through the water. If visual contact was established, Walker would execute an attack run using depth charges or acoustic homing torpedoes, depending on whether the submarine was surfaced or submerged. The psychological advantage of radar detection was enormous. U-boat commanders operating according to traditional doctrine believed they were invisible when submerged or during night surface transit. The sudden appearance of aircraft directly overhead with no prior warning created confusion and panic that disrupted tactical responses. Submarines that might have successfully evaded attack through immediate crash dives or defensive fire found themselves under attack before their commanders understood they had been detected. The time compression from detection to weapon release left U-boat crews with virtually no margin for effective countermeasures. Walker's patrol on March 22, 1943, illustrated the devastating effectiveness of centimetric radar against submarines operating with obsolete tactical assumptions. The radar operator detected a contact at 13 miles range, bearing 270 degrees during a routine patrol pattern south of Greenland. The contact appeared as a strong return that persisted across multiple radar sweeps, indicating a solid target rather than false echo from wave action. Walker altered course to intercept, while descending to attack altitude. Visual identification at 6 miles confirmed the target was a Type 7C U-boat proceeding on the surface at approximately 15 knots. The submarine's conning tower was clearly visible in the early morning twilight, with lookouts scanning the horizon for approaching threats. The submarine showed no indication of radar detection or awareness that an aircraft was approaching from astern. Walker positioned his Liberator for an attack run from directly ahead of the submarine's course, minimizing the time the U-boat would have to dive once the aircraft was spotted. The attack commenced at 2,000 feet altitude, with Walker's bombardier releasing 6 depth charges in a stick pattern calculated to bracket the submarine's position. The submarine's lookouts spotted the approaching aircraft at approximately 1 mile range, and the U-boat began an emergency dive with klaxons sounding throughout the hull. The depth charges detonated as the submarine's conning tower disappeared beneath the surface, creating massive water columns that obscured the target area for several seconds. Walker circled the attack position and observed a large oil slick spreading from the point where the submarine had submerged. Debris, including wooden planking and what appeared to be personal items, surfaced within the oil slick, indicating the submarine had sustained significant damage. The crew maintained surveillance of the area for 30 minutes, but observed no further signs of the submarine surfacing or evidence of survivors. The engagement was later assessed as a probable kill, with the submarine identified through intelligence correlation as U-384. The efficiency of the engagement typified how thoroughly centimetric radar had transformed anti-submarine warfare. From initial radar detection to weapon release had required less than 12 minutes, with the submarine crew having virtually no warning that they were under attack until the final moments before depth charge impact. The tactical advantage that darkness and weather conditions had provided to U-boats throughout the early war years had been negated by technology that allowed Allied aircraft to hunt submarines with precision, regardless of visibility conditions. The strategic impact of this technological shift became apparent in the Atlantic battle statistics for spring 1943. U-boat losses spiked dramatically as more Allied aircraft received ASV Mark III installations, and crews gained proficiency in radar-directed attack procedures. In May of 1943 alone, German submarine forces lost 41 boats, an unsustainable attrition rate that forced Admiral Dönitz to temporarily withdraw U-boats from North Atlantic operations. The campaign that had nearly severed Britain's maritime lifeline had been decisively defeated by a combination of improved convoy protection and radar technology that German forces couldn't counter. Walker's squadron compiled attack records that demonstrated the dramatic improvement in aircraft effectiveness after receiving centimetric radar equipment. During 6 months of operations with ASV Mark II meter-wave radar, the Boer squadron had achieved 4 confirmed U-boat kills from 37 contacts. After transitioning to ASV Mark III, the squadron recorded 18 confirmed kills from 43 contacts over a comparable operational period. The improvement in kill-to-contact ratio from roughly 10% to over 40% illustrated how profoundly the detection capabilities had shifted tactical outcomes. The operational limitations of ASV Mark III were relatively minor compared to its detection advantages. The equipment required careful maintenance to prevent magnetron failures that would render the radar inoperative. The power supplies generated substantial heat that required ventilation management in the aircraft's electronics bay. The rotating antenna mechanism occasionally jammed, requiring manual cranking by crew members to restore scanning function. Despite these technical challenges, the reliability of centimetric radar systems greatly exceeded the meter-wave equipment they replaced. British scientists continued refining the cavity magnetron design throughout 1943 and 44, improving power output and operational lifespan. The manufacturing processes were simplified to enable increased production rates as demand for radar-equipped aircraft expanded across multiple theatres. American industry began producing magnetrons under British license, eventually exceeding British production capacity and supplying radar systems for US Navy anti-submarine aircraft operating in the Atlantic and Pacific. The German submarine base at Lorient on the French Atlantic coast reflected the grinding attrition that centimetric radar had inflicted on U-boat operations by autumn of 1943. Captain Lieutenant Werner Hartmann walked through the concrete bunkers where mechanics worked on submarines returned from patrol, noting the visible battle damage that marked nearly every boat. Shell holes patched with welded plate, diving plane mechanisms, bent from depth charge near misses, conning towers scarred by aircraft cannon fire. The physical evidence told a story that official casualty reports tried to obscure through statistical manipulation. Hartmann had survived his March encounter with the British Liberator west of Iceland, but U-262 had sustained damage severe enough to require 6 weeks of yard repairs. During his forced stay at the Lorient base, he interviewed commanders from other boats and compiled a disturbing pattern of detection incidents that suggested Allied aircraft possessed capabilities far beyond what German intelligence acknowledged. Submarines were being attacked during new moon periods when visual detection should have been impossible. Aircraft were appearing directly overhead with no advance warning, as if guided by precise navigation to submarine positions. Evasive maneuvers and tactical deception that had worked successfully in 1941 and early 42 were proving completely ineffective. The briefing rooms at Lorient displayed charts showing U-boat patrol areas and convoy routes, but the tactical discussions now focused primarily on survival rather than offensive operations. Commanders shared techniques for minimizing surface time, debated optimal diving depths to avoid radar detection, and speculated about countermeasures against the mysterious Allied detection capabilities. The psychological burden on submarine crews was visible in the faces of men returning from patrol. The confident aggression that had characterized U-boat service in the early war years had been replaced by defensive caution and barely concealed fear. Fregattenkapitän Günther Hessler arrived at Lorient in October of 1943 to conduct operational assessments for Admiral Dönitz's staff. Hessler had commanded U-boats during the successful Atlantic campaigns of 1940 and understood submarine warfare at both tactical and strategic levels. His interviews with returning commanders revealed consistent patterns that German naval intelligence could no longer dismiss as coincidental or imagined. Allied aircraft were detecting submarines through some method that functioned in complete darkness, penetrated cloud cover, and operated at ranges that exceeded visual capabilities by enormous margins. Hessler's report to Dönitz documented specific incidents where submarines had been attacked within minutes of surfacing in conditions of total darkness and heavy weather. The aircraft approach bearings suggested they had detected the submarines while still at considerable distances, allowing time to maneuver into optimal attack positions before the U-boat's lookouts could spot the approaching threat. The only technology that could explain these capabilities was radar operating at wavelengths significantly shorter than the meter-wave systems German intelligence had previously identified. The captured British equipment from HMS Metabele had provided physical proof that Allied forces possessed centimetric radar, but German technical response had been catastrophically slow. Kriegsmarine research facilities lacked the industrial infrastructure and specialized expertise to rapidly develop equivalent systems or effective countermeasures. The cavity magnetron design required precision manufacturing capabilities that German industry, already strained by competing military production priorities, couldn't quickly duplicate. The scientific knowledge existed within German research institutions, but the engineering development and production scaling would require years rather than months. Dönitz faced strategic choices that all involved accepting significant operational limitations. U-boats could no longer operate effectively in areas where Allied air coverage was intensive. The tactics that had allowed submarine wolf packs to devastate convoys now exposed the submarines to unacceptable attrition. The technological advantage had shifted so decisively to Allied forces that continuing Atlantic operations using existing U-boat designs and tactics would accomplish nothing except the death of increasingly irreplaceable submarine crews. The German response focused on defensive measures that acknowledged technological inferiority while attempting to reduce operational vulnerabilities. U-boats were equipped with additional anti-aircraft guns to provide defensive fire against attacking aircraft, though the guns proved largely ineffective against aircraft that could initiate attacks from outside the range where submarines could effectively return fire. Submarines received instructions to remain submerged whenever possible, surfacing only when absolutely necessary for battery charging, and then only in weather conditions that might limit aircraft operations. German scientists developed the Naxos radar detector, a receiver designed to detect Allied radar transmissions and provide warning to submarine crews that they were being tracked. The Naxos equipment could identify centimetric radar signals and alert commanders before aircraft closed to visual range, theoretically allowing time for emergency dives. In practice, the warning time was often insufficient for submarines to reach safe depths before depth charges arrived. The physics of submarine diving were unforgiving. Even a crash dive required 45 to 60 seconds to get the boat underwater and another 2 to 3 minutes to reach depths where depth charges lost effectiveness. Hartmann's U-262 received Naxos equipment in January of 1944 before departing on patrol to the western approaches. The detector consisted of a receiver unit with a simple warning light that illuminated when centimetric radar signals were detected. The equipment was mounted in the conning tower, where the officer of the watch could monitor it during surface operations. Hartmann tested the system during the transit from Lorient, confirming that it provided warnings when patrol aircraft passed within radar range, but the utility was limited by the fact that detection meant the submarine was already being tracked and attack was probably imminent. The patrol demonstrated how completely Allied radar dominance had transformed Atlantic operations. U-262 spent 16 days at sea and achieved exactly 0 attacks against merchant shipping. The submarine remained submerged for all but 4 hours of the entire patrol, surfacing only at night during brief periods when Naxos indicated no radar signals in the area. The battery capacity limited submerged speed to 4 knots for extended periods, reducing the submarine's ability to intercept convoys or maneuver to attack positions. When surfaced, the crew maintained constant vigilance on the Naxos detector, diving immediately whenever the warning light indicated radar contact. The psychological impact on the crew was severe. The constant threat of sudden attack from aircraft that the Tectory 7D could appear without warning created stress levels that affected operational effectiveness and crew morale. Submariners who had volunteered for U-boat service, seeking the aggressive hunting operations of the early war years, found themselves trapped in steel tubes beneath the Atlantic, unable to fight effectively against an enemy they couldn't see or counter. The casualty rates made U-boat service the most dangerous duty in the German military, with statistical life expectancies for submarine crews measured in single-digit months. British Operational Research Section analysts compiled data on U-boat kill rates correlated with aircraft radar equipment types, documenting the dramatic effectiveness improvements associated with centimetric systems. Aircraft equipped with ASV Mark III achieved kill rates approximately 4 times higher than aircraft operating with meter-wave radar or visual detection methods alone. The statistical analysis confirmed what operational commanders had observed empirically. 10-centimeter radar had fundamentally altered the tactical balance in anti-submarine warfare. The geographic scope of Allied air coverage expanded throughout 1944 as more aircraft received centimetric radar installations and additional air bases came online to close gaps in convoy protection. The mid-Atlantic air gap that had provided U-boats with relatively safe operating areas during 1942 was eliminated through combination of very long-range aircraft and escort carriers, providing localized air cover for convoy groups. U-boats attempting to concentrate against convoys found themselves under nearly continuous air attack from aircraft that could detect submarines faster than the boats could maneuver into attack positions. The introduction of acoustic homing torpedoes gave Allied aircraft even more lethal capabilities against detected submarines. The Mark 24 mine, actually an air-dropped acoustic torpedo, could be released at considerable distances from a submarine contact and would home in on the sounds of the submarine's propellers and machinery. Aircraft equipped with both centimetric radar for detection and acoustic torpedoes for attack could engage submarines from standoff ranges that eliminated the need for precision depth charge placement. The combination of technologies created overlapping capabilities that covered the entire engagement sequence from initial detection through final attack. German countermeasure development lagged so far behind Allied capabilities that by the time defensive systems entered service, the Allies had developed additional technologies that negated the countermeasures. The Aphrodite balloon decoy system used metallized balloons released from submarines to create false radar targets and confuse Allied aircraft. Testing showed the balloons did create radar returns, but Allied operators quickly learned to distinguish between balloons drifting with wind and actual submarines. The countermeasure achieved nothing except consuming resources that could have been allocated to more effective defensive systems. The strategic situation deteriorated further as Allied forces invaded France in June of 1944, threatening the submarine bases along the French Atlantic coast that provided forward deployment for U-boats operating against Atlantic convoys. The Lorient and Saint-Nazaire bases that had served as primary U-boat facilities since France's fall in 1940 were within range of Allied tactical aircraft and came under increasing air attack. The massive concrete bunkers provided protection for submarines during refit, but the deteriorating strategic situation made sustained operations from French bases increasingly untenable. Dönitz withdrew surviving U-boats from French bases in August of 1944, relocating operations to Norwegian ports that remained under German control but were significantly farther from primary Atlantic convoy routes. The increased transit distances meant submarines spent more time traveling to and from patrol areas and less time on operational stations where they could engage Allied shipping. The geographic disadvantage compounded the technological inferiority, reducing U-boat effectiveness to levels where the campaign's continuation served primarily to tie down Allied anti-submarine forces, rather than inflict significant damage on merchant traffic. The Type 21 U-boat represented German engineering's attempt to regain technological parity through revolutionary submarine design, rather than incremental improvements to existing boats. The new submarines incorporated streamlined hulls, optimized for submerged performance, substantially increased battery capacity for extended underwater operation, and schnorkel systems, allowing diesel engine operation while submerged at periscope depth. The design philosophy acknowledged that submarines could no longer operate effectively on the surface and needed capabilities for conducting entire patrols while submerged. The Type 21 promised submerged speeds exceeding 16 knots, fast enough to overtake convoys and maneuver into attack positions without surfacing. The battery capacity allowed sustained high-speed operation that would enable the submarines to evade pursuing escorts after attacking. The schnorkel system theoretically allowed unlimited submerged endurance limited only by crew factors and supplies rather than battery depletion. The combination of capabilities could have restored German submarine effectiveness, despite Allied radar superiority, but the Type 21 entered service too late and in too few numbers to influence the war's outcome. Production challenges delayed Type 21 deployment until the final months of the war, when German industrial capacity was collapsing under Allied strategic bombing and the advancing Soviet ground offensive. The sophisticated manufacturing techniques required for the new submarine design exceeded the capabilities of bomb-damaged shipyards, working with increasingly scarce materials and forced labor drawn from concentration camps. The handful of Type 21 boats that became operational conducted limited patrols that demonstrated their technical capabilities but achieved negligible strategic impact. The broader industrial competition between German and Allied production capabilities had been decisively won by the Allies long before the Type 21 could enter service in meaningful numbers. Allied shipyards were producing escort vessels and aircraft faster than U-boats could sink them, while German submarine construction struggled to replace boats lost to Allied air and surface attacks. The cavity magnetron that enabled centimetric radar represented just one element of Allied technological and industrial superiority that German forces couldn't match through innovation or determination. Hartmann's final patrol in April of 1945 illustrated the complete futility of continued U-boat operations against Allied forces that possessed overwhelming advantages in detection technology, weapons systems, and numerical strength. U-262 departed from Kristiansand, Norway, with orders to patrol shipping lanes west of Scotland, but encountered continuous air surveillance that prevented effective operations. The submarine spent 23 days submerged, surfacing only 3 times for brief periods when Naxos indicated temporary absence of radar contacts. 0 attacks were executed, 0 targets were even sighted. The patrol accomplished nothing except consuming fuel and supplies while exposing the crew to constant danger for no military purpose. The German surrender in May of 1945 ended the Atlantic U-boat campaign that had cost over 30,000 German submariners their lives and destroyed more than 700 submarines. The Allied victory in the Battle of the Atlantic resulted from multiple factors, including improved convoy tactics, increased escort vessel production, and enhanced anti-submarine weapons. But the introduction of centimetric radar represented the single most decisive technological advantage that transformed the campaign from uncertain struggle to Allied dominance. The 10-centimeter wavelength that German intelligence had assessed as impractical had proven to be the key to defeating the submarine threat that had nearly severed Britain's maritime lifelines. The captured German submarines and their crews provided Allied intelligence with a comprehensive understanding of how completely the Kriegsmarine had failed to develop effective countermeasures against centimetric radar. Interrogations revealed that German commanders had never fully understood the capabilities they faced, attributing their detection to various causes including spies, direction-finding systems, and even speculative technologies like infrared detection. The true explanation, that Allied aircraft could detect periscopes at 8 miles using 10-centimeter radar, had seemed so technically impossible to German engineers that they never seriously considered it until captured equipment provided undeniable proof. Professor John Randall's cavity magnetron, developed in the Birmingham University laboratory and refined through intensive British and American engineering efforts, had achieved strategic effects that rivaled any weapons system deployed during World War II. The technology had enabled Allied forces to neutralize the U-boat threat without engaging in the mathematically impossible task of searching vast ocean areas through visual observation or meter-wave radar. The electromagnetic physics that allowed 10-centimeter wavelengths to detect small targets with precision had translated directly into thousands of Allied merchant seamen who survived voyages that would have ended in torpedo attacks, without the radar protection. The post-war technical analysis, conducted by Allied intelligence teams, examined captured German radar research and countermeasure development, revealing how far behind German technology had fallen despite the Kriegsmarine's early advantages in submarine design and tactics. German scientists had understood the theoretical principles of centimetric radar, but lacked the industrial capacity and engineering expertise to rapidly develop operational systems. The cavity magnetron production required specialized manufacturing techniques that Germany's bomb-damaged industrial infrastructure couldn't replicate on the scale necessary for widespread deployment. The strategic lessons of the Atlantic radar competition extended far beyond submarine warfare to influence Cold War military development and doctrine. The recognition that technological surprise could decisively shift operational advantages prompted both superpowers to invest heavily in research programs designed to maintain technical superiority across multiple domains. The cavity magnetron's success demonstrated that fundamental scientific breakthroughs could be rapidly translated into operational capabilities that rendered existing military systems obsolete, regardless of numerical or tactical advantages. The human dimension of the radar revolution remained largely invisible in official histories that emphasized tonnage statistics and kill ratios. The submariners who died because their commanders couldn't understand why traditional tactics no longer worked faced death in explosions that came without warning from aircraft they never saw. The Allied aircrews who successfully attacked submarines using centimetric radar often never knew whether their depth charges had achieved kills or merely forced submarines to evade. The individual experiences of technological warfare's revolution were subsumed into aggregate statistics that obscured the fear, confusion, and sudden violence that characterized the Battle of the Atlantic's final years. Werner Hartmann, survived the war and spent 18 months in British captivity before repatriation to Germany in late 1946. During interrogation, he provided detailed accounts of his patrol experiences, including the March 1943 detection incident that had convinced him Allied forces possessed capabilities beyond German intelligence assessments. The interrogators showed him photographs of ASV Mark III radar installations and explained the cavity magnetron technology that had enabled detection of his periscope from 8 miles in total darkness. Hartmann's reaction combined professional respect for the engineering achievement with bitter recognition that German naval leadership's intelligence failures had condemned thousands of his fellow submariners to preventable deaths. The declassification of wartime radar development programs during the 1970s finally revealed the full scope of Allied technological advantages and German intelligence failures. The cavity magnetron that Professor Randall had developed in 1940 had remained classified for 3 decades after the war ended, protected by security restrictions that prevented public understanding of how thoroughly radar had dominated the Atlantic battle. The technical details of centimetric radar systems, the production challenges overcome by British and American industry, and the operational effectiveness achieved against submarines all remained unknown to general audiences until historical researchers gained access to declassified archives. David Walker, the RAF pilot who had conducted numerous successful attacks using ASV Mark III radar, participated in post-war studies examining the effectiveness of airborne anti-submarine systems. His operational experience provided valuable data for analysts assessing the impact of radar technology on maritime warfare outcomes. The statistical analysis confirmed that aircraft equipped with centimetric radar achieved submarine detection, rates approximately 8 times higher than aircraft limited to visual search methods, directly validating the operational significance that commanders had observed during the war. The cavity magnetron technology transitioned to civilian applications after military security restrictions were gradually lifted. The microwave radiation generation principles that had enabled submarine detection formed the foundation for commercial radar systems used in aviation, maritime navigation, and weather observation. The manufacturing techniques developed for wartime magnetron production influenced post-war electronics industry practices, particularly in vacuum tube design and precision metal machining. The scientific understanding of microwave physics that had been advanced through radar research contributed to subsequent developments in telecommunications and eventually microwave cooking technology. The Battle of the Atlantic's technological dimension represented a case study in how scientific research translated to military capability through intensive engineering development and industrial production. The timeline from Randall's cavity magnetron breakthrough in February 1940 to operational ASV Mark III deployment in mid-1942 demonstrated remarkable efficiency in moving laboratory prototypes to frontline systems. The British and American industrial mobilization that produced thousands of radar sets within 2 years of initial development showed organizational capabilities that Germany's fragmented research establishment and bomb-damaged factories couldn't match. The strategic consequences extended beyond the immediate tactical advantages in submarine detection. The Allied success in rapidly developing and deploying centimetric radar created technological momentum that influenced subsequent weapons development and shaped post-war military planning. The recognition that electromagnetic spectrum dominance could provide decisive advantages in detection and targeting drove massive investments in radar, electronic warfare, and communications systems that defined Cold War military competition. The principles established during the Battle of the Atlantic's radar revolution remained relevant through decades of technological evolution. The human cost of Germany's radar intelligence failure was measured not only in dead submariners but also in the Allied merchant seamen and naval personnel who would have died in torpedo attacks if U-boats had maintained their early war effectiveness. The statistical analysis suggested that continued U-boat success at 1941 and early 1942 loss rates would have sunk sufficient merchant tonnage to potentially force British surrender, or at minimum, delay the Allied build-up necessary for D-Day invasion operations. The centimetric radar that enabled Allied anti-submarine dominance after mid-1943 contributed directly to Allied victory in Europe by protecting the maritime supply lines that sustained British resistance and enabled American force deployment. The technological surprise that German U-boat commanders experienced when first encountering centimetric radar detection had parallels throughout military history, where intelligence failures prevented effective responses to innovations. The combination of technical skepticism from German engineers, who believed centimetric radar was impractical, intelligence analysis that dismissed operational reports as exaggerated, and industrial incapacity that prevented rapid countermeasure development created conditions where Allied technological advantage could be fully exploited before German forces understood the nature of the threat they faced. The legacy of the cavity magnetron and ASV Mark III radar extended far beyond World War II submarine warfare to influence fundamental approaches to military technology development and operational security. The recognition that scientific breakthroughs could be concealed through security restrictions and rapidly deployed to achieve surprise advantages shaped Cold War research programs on both sides of the Iron Curtain. The lessons learned from the Atlantic radar competition informed strategic thinking about technological innovation, intelligence collection, and the relationship between scientific research and military capability. Werner Hartmann's experience aboard U-262 represented the perspective of thousands of German submariners who faced Allied technological superiority without understanding its source or scale. The mysterious detections that seemed to defy physical possibility, the aircraft attacks that appeared without warning, and the complete ineffectiveness of traditional evasion tactics combined to create psychological burden that undermined operational effectiveness even among experienced crews. The knowledge that death could arrive instantly from threats that couldn't be seen or countered transformed submarine service from aggressive hunting operations to defensive survival missions. The post-war interviews with Allied radar operators and German submarine commanders provided historians with contrasting perspectives on the same technological revolution. British and American aircrews described the satisfaction of detecting submarines at long ranges and executing precise attacks against targets that never knew they were being tracked. German submariners recalled the terror of sudden depth charge attacks during darkness, the paranoid vigilance of surface watches, and the gradual realization that their tactical doctrine had become obsolete. The technological gap between detection capability and understanding of that capability created asymmetric warfare conditions, where one side possessed advantages the enemy couldn't effectively counter because they didn't fully comprehend them. The cavity magnetron that enabled centimetric radar represented more than incremental improvement over existing detection systems. The technology constituted a qualitative breakthrough that changed fundamental parameters of maritime warfare by extending detection ranges, improving resolution, and enabling all-weather operations that eliminated the environmental factors submarines had exploited for protection. The physics of 10-centimeter wavelength radar provided capabilities that German forces couldn't match through tactical innovation or operational adaptations, because the advantages were embedded in electromagnetic principles, rather than procedural factors that could be countered through changed behavior. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.